Okay, so let's continue where we stopped off last class. So in the last class, I introduced the AdaBoost algorithm, which is one particular way of boosting base classifiers to get an improved classifier. So you have a base hypothesis class which consists of predictors that you can learn efficiently, but they have very poor approximation error. They do only just better than a random guess. All right. So the AdaBoost algorithm tries to obtain a classifier that can be expressed as a linear combination of base classifiers, and it turns out that this can actually achieve vanishing training error. All right. So in the AdaBoost algorithm, we start with a distribution on the data points. We initially start with a uniform distribution on data points, and then at each step we keep updating the distribution in some particular way. All right, and so the high level idea is, in each step, given the distribution that you constructed in the previous step, you select the empirical risk minimizer from the base class corresponding to this distribution on the data points. So in iteration t, you select the ERM corresponding to the distribution p t minus 1. Right, so that gives you a HTB, which has a probability of error that we know is going to be strictly less than a half. And based on these, you choose certain parameters and you update the distribution to get pt plus 1. Right? And finally, so at the end of, let's say, capital T steps, you have a bunch of base classifiers, H1, H2, H3 up to H capital T. And the final classifier is just sign of a linear combination of these base classifiers that we constructed at each step. Right? And the high level idea of selecting these distributions is that we choose the distribution at the tth step to be such that it gives higher weightage to those points which were predicted wrongly by the classifier in the tth step. Right? So in pt plus 1, pt plus 1 of xi is going to be greater than pt of xi if ht of xi differs from yi. And if it is the same as that of yi, if it predicts this correctly, then you give it a slightly lower weightage. So the sign in the exponent is going to be positive if you have misclassification, and the sign is going to be negative if it is classified correctly. So that appropriately weights the corresponding points higher or lower. All right. And the hope is that in the next step, since there's a higher likelihood and there's a higher probability that is associated to that particular point, the classifier that is constructed in the next step is hopefully going to classify this point correctly. Right? So eventually all of the points are going to be classified correctly. And in the last class, we also showed that the training error at the end of t steps decays as the number of steps goes to 0, and in fact it decays exponentially in the number of steps. So all of this was with respect to the training error. Right? So far we've said nothing about the generalization error, or in general the generalization capabilities of AdaBoost. So we'll explore that in a little bit of detail today. So first we'll see what is the VC dimension of a classifier that is obtained using a technique such as AdaBoost. Right? So the real hypothesis class of interest is the following. So suppose that we are given a base hypothesis class B, and let's assume that the VC dimension of the base hypothesis class is equal to D, for some positive integer D. Now using this, we'll construct the following hypothesis class, which is basically all possible outputs that we can get at the end of T steps. Right? So at the end of T steps, we will see a classifier or a predictor that looks something like this: summation T equal to 1 to capital T alpha T H B T of X for so irrespective of how what the trajectory of AdaBoost looks like, you end up at the end of T steps, you end up with a predictor that looks something like this, right? So you can think of this as taking capital T predictors from the base hypothesis class and composing that with a linear classifier, right? That's basically what this is doing. And in fact, we'll make use of this property in deriving an upper bound on the VC dimension. So here's the main result. The VC dimension of this hypothesis class can be upper bounded by T times D plus 1 times 3 log to base E of T times D plus 1 plus 2. So in today's class, I'll prove something that's similar, but I won't be worried about the explicit constants. We'll just see that this is T times order T times D plus 1 log T times D plus 1. All right. Getting the exact constants just involves optimizing the right bounds, which just requires a little more calculus. But I just want to give the main ideas behind the proof. So let's recall the definition of the VC dimension first. So the VC dimension is the largest set that is shattered by the hypothesis class. All right. So let's suppose that Xm is a set that is shattered by the hypothesis class that we're interested in. All linear combinations of T base classifiers. Okay. So firstly, as we've noted previously, any predictor within L is a composition of these two maps. You first take the following vector of the predictions that you obtain using t different base classifiers, and then a linear classifier, right? So if I take one particular base classifier, so let's consider how many different labelings can we get? The number of possible labelings of xm by predictors in B. In the base hypothesis class. Right? Note that the VC dimension of L could be much larger than the VC dimension of B, and M therefore could be much larger than the size of the largest set that is shattered by B. So how many possible labelings can I get? Or what would I use to upper bound the number of possible labelings that you can get for the set xm by the base hypothesis class B? Is there something you've seen before? The question is, I want to know, I have this set x1 through xm. It consists of m points. And I want to know how many possible configurations, how many possible labelings can I get for this set using hypothesis from B. Exactly. So it's the growth function, right? So this is upper bounded by the growth function. And what is an upper bound for the growth function in terms of the VC dimension? Okay, so it's E times the number of points in the set by D whole to the power D. That's an upper bound on the growth function in terms of the VC dimension. This is what we use, this is what we get basically using the Sauer-Shelah lemma. Right? So this is the number of possible labelings that we can get using predictors from these points, from B, right? So if I look at, so if I consider the map xm to h1b of x1 up to ht b of x1 h2b of h1b of x2 htb of x2 and so on for the n different points, right? By varying h1, h2 up to ht, how many possible configurations can I generate? Now, there are at most em by d whole to the power d possible distinct configurations that I can get using one predictor. So out of these, I'm supposed to choose t of them. So the number of distinct configurations or labelings is at most em by d whole to the power d, choose t, and this is upper bounded by, we'd use a very loose upper bounds. This is at most em by d whole to the power of d times t. So there are these many possible labelings that I can generate for these m points. And remember, each labeling is itself is a t-length vector. Right? So on each of these, I have to now apply a linear predictor. Right? So I have m points, and for m points, how many possible distinct labelings can I get? So this linear classifier is in what dimension? T dimensions, right? And what is the VC dimension of a linear classifier in T dimensions? T plus 1. In this case, it's a homogeneous linear classifier. So the VC dimension is T. And therefore, how many possible configurations can the linear classifier generate? But then, you know that there's the VC dimension. You know what the VC dimension is. It is at most 2 to the power t, but can potentially be lower. Because m could be much larger than 2 to the power t, right? M is the size of the largest set that is shattered by the hypothesis class. So I'm sorry. So m could potentially be smaller than 2 to the power t.
M is the size of the
yeah. So m is the size of the set that is shattered by the composite hypothesis class, right? And I want now basically each point, each of these m points is now mapped to a t length vector, right? And I'm considering a linear predictor for this, right? The hypothesis class of all linear predictors. So how many distinct configurations can you generate in general? So let's fix some m, all right? For now, m is some integer. I pick some m points, x1 through xm, right? And this is going to be the set that is shattered by L of b comma t, which is the set of all predictors that can be expressed as a linear classifier composed with T base classifiers. Right? Now I fix these m points. For now, let's not worry about what these m points are. I want to know, if I want to get a bound on the VC dimension, I need to know how many possible distinct labelings I can generate by varying h1 through ht and alpha 1 through alpha t. Right? So now I'll treat these two problems independently. First, I'll see how many possible configurations I can get just by varying h1 through ht. And then I'll see how many possible distinct configurations I can get by varying alpha 1 through alpha t. All right? By varying h1 through ht, I can get these many distinct configurations. All right? So for each configuration, let me now see how many possible configurations or labelings I can get just by varying alpha 1 through alpha t. Right? So what is the number of distinct labelings we can generate it's some point x1 through xm, right?
This one.
Sorry, which one? Yeah, x1 with h1, h2, h3 up to ht. Right, that's the first part of the composition. And then I'm going to take a linear combination of these and apply sign. Right? So each xi is being mapped to these t points. So xi could be some, L dimensional vector. Now I'm mapping each L dimensional vector into a T dimensional vector through h1 through ht. Right? Of course, this is now restricted because each hi can take only values +1 or -1, but I'm not going to worry about that. So effectively, for each choice of h1 through ht, because I can now vary h1 through ht over all possible choices from the base hypothesis class. But for a particular h1 through ht, I'm going to get n vectors, each vector having dimension t. Right? So this is some particular xm prime. Right? Now for this xm prime, how many possible labelings can I generate using purely linear classifiers? That is, by varying just alpha 1 through alpha t for fixed h1b through htb. They're basically the same. Right? So once again, this is just upper bounded by the growth function of linear classifiers. And the VC dimension for the linear classifier is t. Therefore, this is upper bounded again by the Sauer-Shell lemma by em by t whole to the power t. So the number of possible labelings I can generate just by varying h1 through ht is these many, right? And the number of possible distinct labelings I can generate by varying only alpha for a fixed choice of h1 through ht is at most this particular quantity. So if I compose the two, how many possible distinct labelings can I generate? Product of the two, right? It's a loose upper bound, but that's okay. So the number of distinct labelings generated by L of Bt is upper bounded by the product of those two, which is Em by T whole to the power T times Em by D whole to the power of D times T. We'll assume that both D and T are greater than or equal to E, just so that things look a little more convenient. So if both T and D are greater than E, E by T is at most 1 and E by D is also at most 1. So this is at most m to the power t times m to the power dt, which is m to the power of t times d plus 1. Right? So these are so for any set x1 through xm, this is the maximum number of distinct labelings that can be generated. Can't be any more than this. Right? For this to be a set that is shattered by the hypothesis class, what should this be equal to? So if xm is shattered by L of b comma t, then what should happen? How many distinct labelings should you see? Two to the power m, right? So the number of distinct configurations should be 2 to the power m. So 2 to the power m should be obviously be less than or equal to m to the power of t times d plus 1, right? Or equivalently, log or m should be less than or equal to log m times t times d plus 1, or m by log m should be less than or equal to t times d plus 1, or equivalently m should be less than or equal to t times d plus 1 log t times d plus 1 up to some constant. Okay. Let's maybe go over through the high level idea behind this. So essentially what I want to do is derive an upper bound on the VC dimension of the set of all possible predictors that can be written as a composition of t-based classifiers and a linear classifier, right? So to get an upper bound on the VC dimension, I'll take a set that is shattered by this hypothesis class L of b comma t. So if I take any set that is shattered by L of b comma t, then by varying h1 through ht and alpha 1 through alpha t, I should be able to generate all possible 2 to the power m distinct labelings of these m points, right? So if m is the VC dimension of L, then by varying all of these parameters, I should be able to generate all possible 2 to the power m labelings. So for any given set of size m, let us try to see how many possible labelings I can possibly generate. What is the maximum number of labelings I could possibly generate by varying h1 through ht and alpha 1 through alpha t. So if I fix a particular alpha 1 through alpha t, the number of possible labelings I can generate just by varying h1 through ht is at most this particular quantity, em by d whole to the power of dt, right? And if I fix h1 through ht, then the number of possible labelings I can generate by varying just alpha 1 through alpha t is at most em by t whole to the power t. In getting both, we just made use of the growth function and the fact that we knew the VC dimension of each of these component classifiers. We know that the VC dimension of the base classifier is d, and the VC dimension of linear classifiers is equal to the ambient dimension, which in this case is equal to t, right? So, and if the VC dimension is, let's say, t, then the growth function is at most em by t whole to the power t. This comes from the Sauer-Scheller lemma. So we just made use of the fact that, okay, we know the VC dimension and therefore we know the growth function. So the overall growth function should be at most the product of the growth functions, because the number of possible labelings that you can generate by varying two sets of parameters is at most the number of labelings you can generate only by varying one parameter times the number of labelings you can generate only by varying the other parameter, right? And the product of those two simplified turns out to be m raised to at most m raised to t times d plus 1. And since the number of possible labelings we can get is 2 to the power m, because it's a set that is shattered by L, 2 to the power m cannot exceed m to the power of t times d plus 1, and that's how we get m less than or equal to some constant times t times d plus 1 log t times d plus 1. All right. Again, in the last step, I didn't worry about the hidden constants involved, but just going from this step to this step, you can explicitly find the constants involved, and you can show that this is at most t times d plus 1, 3 times log of t times d plus 1 plus 2. All right, that's just if let's say log m by m is at most alpha, then m is at most alpha times 3 log alpha plus 2. All right. Any questions? So this gives an upper bound on the VC dimension of AdaBoost. But the problem is that the VC dimension of AdaBoost grows as the number of steps grows. As t tends to infinity, the VC dimension also tends to infinity. And that's a problem because now if I want to drive the training error down to 0, then I must increase t. But if I increase t, then the VC dimension increases and potentially the gap between the generalization error and the empirical risk could also grow. So at least our bounds become weaker and weaker as t becomes larger and larger. Right? And as the VC dimension increases, the number of the sample complexity will also increase. And that is a problem. So purely VC dimension based bounds can't really explain the actual the practical performance that we observe. So instead, there are other bounds on the generalization error that one can derive using the concept of margin. So I'll just state the result without going through the proof. But here's a margin based bound on the generalization error. So you can show that the probability that R of h, the generalization error, is less than or equal to R hat s comma rho of h. I'll define what this quantity R hat s rho of h is, plus 2 by rho. So rho is some parameter that is greater than 0, and this bound holds true for every parameter rho, as we'll see. Root 2d log en by d whole divided by n plus square root log 1 over delta by 2n. So this probability that this holds true for all h, which can be written as a convex combination of base classifiers, any number of base classifiers, is greater than or equal to 1 minus delta. Where this R hat of s comma rho is kind of a modified version of the empirical risk, but it also takes into account the margin. So we're kind of assuming that the margin is at least rho, margin being defined a little subtly here. So this is the number of points in your training set. So in general, for the 0-1 loss, the empirical risk would be the number of points that are classified incorrectly. Or in other words, yi times hi less than or equal to 0. In this case, I'll define it a little differently. So this is less than or equal to rho. for some rho greater than 0. Where this rho f of x is summation t equal to 1 to capital T alpha t h b of xi or x divided by the L1 norm of alpha. So effectively rho f of x is just a normalized version of the linear predictor, except that I'm normalizing it by the L1 norm instead of the L2 norm that we saw when we discussed support vector machines. All right, so this is the L1 normalized linear predictor, and this is effectively just the margin corresponding to the L1 normalized linear predictor. It's divided by L. So this is the fraction of points for which the margin is less than or equal to rho, with the margin being defined in this slightly different way with respect to the L1 norm rather than the L2 norm. So even if the VC dimension keeps growing, if it's somehow possible to show that this particular L1 margin is large enough, is sufficiently large, then we can obtain a generalization error which behaves like this. And in fact, one can also show the following, that after t rounds of AdaBoost, this particular variant of the empirical risk is in fact at most 2 to the power t times product t equal to 1 to capital T square root of epsilon t whole raised to 1 minus rho times 1 minus epsilon t whole raised to 1 plus rho. So if epsilon t is sufficiently far away from half, epsilon t doesn't have to go down to 0 as t goes to infinity. But if epsilon t is sufficiently small so that for each t, let's say this particular quantity is less than 1, right? Or this particular quantity is strictly less than 2, right? Which is not too much to expect, because let's say if epsilon t is 0.1 for some particular rho, then this would be 0.1 raised to 1 plus rho times 0.9 raised to 1 plus rho whole to the power half, which could be less than half for every t. So if this quantity is strictly less than half, then the right hand side, which is 2 to the power t times something less than half to the power t, goes down to 0 as t goes to infinity. And we know that epsilon t is less, if we have a gamma weak learner in each step, then epsilon t is at most half minus gamma, and 1 minus epsilon t is something like half plus gamma. And in fact, even without that, this quantity is at most 1, right? And this quantity is at most half minus gamma to the power of 1 minus rho. So if you choose rho appropriately based on gamma, you're guaranteed that this is less than half, and therefore if you have a weak learner at each step, then this quantity goes to 0 exponentially in t for some particular rho. Any questions? So AdaBoost was proposed a long time ago, and a lot of the theory behind AdaBoost was originally proposed for decision trees, but several variants and several generalizations of AdaBoost are known, and we'll discuss some of those generalizations, or in other words, another way of looking at AdaBoost. So basically, it's a tree-based approach for classification. You take a series of decisions to classify a particular point. It's one particular hypothesis class. All right. So let's see. Let's take a different viewpoint for AdaBoost that allows several generalizations. All right. So we can view AdaBoost as performing minimization of some particular loss function through a gradient descent type of procedure. Okay. So the basic idea is to view the predictor as one being in some infinite dimensional functional space. So let's suppose that, just for convenience, let's assume that the base hypothesis class is countable. it need not be countable, but just to make some notation more convenient, and to give this particular interpretation as coordinate descent, let's suppose that B is countable. Okay, so therefore you can always write the output of AdaBoost can be written in this particular form. So H theta is equal to sine of summation j equal to 1 to infinity theta j, let's see, h j, let me call this phi j, of x, where each of these phi j is one predictor from the base hypothesis class, ordered in some particular fashion. Okay. So the output of AdaBoost is some predictor which looks like this. But one thing is that the number of non-zero theta j's is at most t. Right? That's what is guaranteed by AdaBoost, because at the end of t rounds of AdaBoost, you get a linear combination of t possible predictors. And the assumption that we are working with is that for every distribution on n samples, there is some j such that the probability of error achieved by phi j on these n samples is at most half minus gamma. Right. So now let's. So this is my final predictor. So let's look at, instead of, so one way to find a predictor of this particular form would be to run empirical risk minimization over the hypothesis class of all possible predictors that can be written in this form. Right? And that's the approach we will take. But instead of using the 0-1 loss, we'll look at a different loss. So one approach, or the general approach, is to minimize one by n summation I equal to 1 to n loss function between yi and h theta of xi, and the minimization is some kind of minimization over theta. But remember that this minimization is over an infinite dimensional space, because the number of parameters theta 1, theta 2, theta 3 and so on are countably infinite. Is this setup clear? So in AdaBoost, instead of taking L to be the 0-1 loss, we choose L to be the exponential loss. choose L of y comma y hat to be e to the power minus y times y hat. So let's define j of theta to be equal to 1 by n summation I equal to 1 to n of e to the power minus yi times y hat, which we are going to take. Let me call this. So choose y comma sine of say h of x, so h bar of x, to be e to the power minus y times h bar x. So this is a specific loss function that we'll choose. N theta j phi j of xi. Or equivalently, this is 1 by n. More generally, this is L of yi h theta of xi. Okay, so the goal is to somehow minimize j of theta with respect to theta, approximately. That's the high level philosophy. Okay, so one way of trying to minimize j of theta is using gradient descent. So you start with a particular theta naught. Remember, theta is an infinite dimensional vector. All right. So one approach is to start with some arbitrary theta naught, or in other words, you pick a particular j, some random j, maybe h1, and set theta 1 equal to 1, and then you find the, so to speak, gradient with respect to j theta, and then perturb it by some particular amount and go on. But again, that's difficult because we're living in infinite dimensional space, so we can't really do that. So one approach is the following: do this so-called coordinate descent, which consists of two steps. The first, you pick one particular coordinate according to some rule. Okay? Pick. So in each step, pick a coordinate j. In the context of AdaBoost, j is chosen such that the probability of error of h jb, or in this case phi j, with respect to whatever distribution is less than or equal to half minus gamma. So you'll only pick one such coordinate which gives a small enough probability of error with respect to the distribution in the tth step. And once you pick the jth coordinate, some particular coordinate j, you only update theta j. You leave all of the other theta i's as it is, but you only update theta j. Only theta j. So theta j star is going to be arg min over theta j of theta. So you have the loss function. You try to minimize the loss function only with respect to theta j. So the final predictor is basically a linear combination, a theta weighted linear combination of base predictors. So in each step, you basically pick one of the predictors from the base predictors, which is guaranteed to give a probability of error less than half, and then update only the weight of the coefficient for that particular predictor by minimizing j of theta. All right. So at every step, you are picking one coordinate in your infinite dimensional space and minimizing and going down the loss function only along that particular direction. Now, going along this direction may not be the best possible direction. If you did pure gradient descent, then potentially you could descend much faster. But this coordinate, this particular choice of coordinate is done so that the loss function decreases. May not be the best direction to decrease, but in this direction there is a decrease. All right, it's not that it is completely flat along this particular direction. So along coordinate j, there is some potential decrease, and along that decrease, you take a step so that you move in along that direction. You take the minimum possible value. Right. So in the case of the loss function that we have, we can explicitly try to minimize what we see. All right. So let's define. Again, we want to minimize j of theta, right? So j of theta is essentially 1 over n summation I equal to 1 to n e to the power of minus yi summation j equal to 1 to infinity theta j phi j of xi. All right, let me call this j prime. So now in the jth step, in the tth step, I only want to update coordinate j. So let me remove all of those components which don't involve j and keep only the components that involve j. This is equal to 1 over n summation I equal to 1 to n e to the power minus yi times summation j prime not equal to j theta j prime phi j prime of xi times e to the power minus yi theta j phi j of xi. Okay, just sort of decoupled the two terms because this quantity is not going to be updated in the current step. Only this theta j is going to be updated in the current step. So my goal is to minimize the right hand side with respect to just theta j. So let me write this as 1 over n summation I equal to 1 to n. Let's call this wi e to the power minus yi theta j phi j of xi. Okay. So the goal is to minimize the right hand side with respect to theta j. We can simplify the right hand side because if you think about it, this particular product y times phi j of xi can either be plus 1 or minus 1 because phi j is a linear predictor. Phi j is a base predictor, it's a base classifier, and therefore that can take values plus 1 or minus 1, and y can take values only plus 1 or minus 1. Right? So let's split these n terms into those terms for which this product is equal to plus 1 and those terms for which this product is equal to minus 1. So this is 1 over n times summation I, which are classified correctly by I such that phi j classifies xi correctly, wi times e to the power of minus theta j plus 1 by n times summation over all I such that phi j does not classify correctly, of wi e to the power of plus theta j. Right? So, I mean, theta j doesn't depend on I anymore. So I can effectively just remove this outside the summation. So this is e to the power minus theta j times, let me call this w plus e to the power theta j times w minus, where w plus is basically this particular quantity and w minus is basically this particular quantity. All right. So now how would you minimize the right hand side? Firstly, what kind of a function is the right hand side? Is it going to be convex or concave? What do you think? How would you check whether this function is convex or concave? What's the most basic test you know to check whether a function is convex or concave? Okay, what is the second derivative of this with respect to theta j? It's the function itself. And what can you say about the function? Is it non-negative, non-positive? So it's non-negative. The second derivative is non-negative. Therefore, the function is convex, right? So since the function is convex, you can just take the first derivative. To minimize this function, you just take the first derivative and set it equal to 0, right? So the minimum, theta j star, to get the minimum, you can take the first derivative and set it equal to 0. So e to the power minus theta j star w plus e to the power plus theta j star w minus should be equal to 0, or theta j star is basically half log w plus by w minus. So this is going to be the update rule in every step, right? But if you sort of work out the details and try to find out what w plus and w minus correspond to, you'll see that in the context of AdaBoost, this ratio w plus by w minus will actually be 1 minus epsilon t by 1 plus epsilon. All right, and these, like each of these, correspond to the distribution on the data points. Right? That's how we interpreted this when we were trying to, when I introduced the algorithm for AdaBoost. So one way of interpreting every step of AdaBoost is performing something like empirical risk minimization. But another way of interpreting AdaBoost is basically running coordinate descent on this particular function. In each step, you pick one particular coordinate that is guaranteed to give you a strictly descending direction, and then try to minimize the function along that particular direction. Any questions? So let's think about different ways in which this can be generalized. Right? This is one interpretation of AdaBoost. And in AdaBoost, we choose the loss function to be the exponential function. And in every step, we basically did coordinate descent. Right? But then there's no particular reason to do this. So for one, you could replace the loss function with something else. Instead of the exponential loss function, you could replace it with something else. Let's say the logistic loss or hinge loss or something else. And in every step, instead of doing coordinate descent, you could do something more similar to gradient descent. You can't do exactly gradient descent. The problem with that is that to do exact gradient descent, you need to be able to find the gradient. But that's not possible because you are working with infinite dimensional space. So there's another variant of this particular technique called gradient boosting. Which works as follows. So you initialize some particular h, So you initialize, let's say, some f0 of x. Let's say you pick something from the base hypothesis class which achieves a probability of error that is strictly less than half. And then for 1, 2, 3, so in t steps, you first compute the following gradient vector, which is basically so in gradient boosting you have some particular loss function y, let me not call this y hat, y comma z, where y is in 1 minus 1 and z could be an arbitrary real number. And I'm assuming that the loss function is differentiable with respect to z. Okay, that's an assumption we'll work with. So you find the gradient, which is minus dou L of y1 z1, the partial derivative with respect to z1, and so on. The ith component is the partial derivative of L of yi zi with respect to zi, and this is evaluated for z1, z2, z3, and so on. Zi is equal to f t minus 1 of xi. So whatever predictor that you got from the previous step, you basically evaluate the gradient with respect to the predictions that you got from your previous step on the n sample points. Where? Okay. Oh, sorry. This should be the, let me take gt to be the negative gradient. Okay. So this is the negative gradient, and once you find the negative gradient, this is some vector, right? Some arbitrary vector which doesn't necessarily correspond to, which doesn't directly give you a predictor from the base hypothesis class. So far, I've not used the base class at all. So the next is to find something from the base hypothesis class, find one predictor from the base hypothesis class that closely approximates the gradient. So you choose HTB to be equal to arg min over all HB from the base hypothesis class, and min over all beta of summation I equal to 1 to n of this g t gti minus h b of xi the whole square. So to find HTB, we're actually solving a regression problem, right? But the regression is done with respect to the gradients at each step. And once you get this, you define rho t to be so now this HTB essentially defines the direction. The direction is taken to closely approximate the gradient, but once you pick this direction, you decide how much to travel along that particular direction. So you take r min over rho, summation I equal to 1 to n of the loss function between yi and f t of xi plus rho times h tb of xi. And ft plus 1 of x is basically ft of x plus rho t times h tb. So at every step, you're taking the predictor that you got from the previous step and then adding something. All right, and this quantity is called a boost. So you're boosting the predictor in one particular direction. At the end of t steps, you get f capital T, and that's going to be the output. Maybe you take the sign of ft to be the final predictor. All right. So this is the basic principle behind gradient boosting, and this can be interpreted as doing approximate gradient descent in this function space. So first you find the gradient of the loss function with respect to z evaluated at the previous set of predictions, and then try to solve a regression to essentially approximately move along that direction. Now there's another approach. Instead of doing gradient descent, you can, if the loss function is twice differentiable, then you can also use Newton's method. So you find the derivative, the gradient, and also the second derivative at each point, and then suitably modify this optimization, this regression problem a little bit, and that leads to another algorithm called XGBoost, which is very widely used in practice today. All right, so one good reference for gradient boosting, one of the early references for gradient boosting, is this paper by Friedman called Greedy Function Approximation. A gradient boosting machine. I think this appeared sometime in 2001 or so. It was one of the early papers to generalize this idea of boosting to, or at least interpret gradient boosting in this particular form. All right. And for here's another paper which talks about Newton boosting, which is the basic principle behind XGBoost. It's a paper titled Gradient and Newton boosting for classification and regression. Any quick questions? Okay, if not, let's stop for today.